Hey folks, my name is Nathan Johnston. Welcome to Lecture 35 of Introductory Linear Algebra. In today's class, we're going to learn how to actually compute the determinant of a matrix. So remember in the previous lecture, we learned what the determinant is. It's this measure of how much the matrix as a linear transformation blows up space, sort of this multiplicative factor by which it expands areas or volumes. Okay, but now we're going to learn how to actually compute it. And the way that we're going to come up with this formula for computing it is we're going to ask the question of, well, what does the determinant, what's the determinant look like on elementary matrices? And the reason for this is, remember back to when we learned about elementary matrices. We learned that every invertible matrix can be written as a product of elementary matrices. Well, because the determinant is multiplicative, if we can figure out what the determinant is for an elementary matrix, then we can just use multiplicativity to figure out how the determinant acts on arbitrary matrices. All right, so that's where we're going one step at a time though. Let's start off, let's really just consider what the determinant of elementary matrices are. Okay, so let's start off with, there are three types of elementary matrices, just consider them one at a time, and we're going to start off with the scalar multiplication elementary matrix. So the elementary matrix corresponding to the elementary row operation C times a particular row. Remember, these elementary matrices, they just look like the identity matrix, except one of their entries is a C along the diagonal, right? The way that you get it is you start with the identity matrix and you do C times row J. Okay, well, so it's diagonal. So remember, like as a linear transformation, sort of what that looks like is it's the linear transformation that's just taking sort of the unit square grid and it's stretching it by a factor of C in one of the directions. Okay, and then we're asking the question, what is the determinant of this matrix? Okay, and based on this picture here, I mean, if the area of this square here is 1, then the area of this rectangle should be, well, it's still got a height of 1, but now its width is C. So its area should be 1 times C, which is C, right? So we think, based on this geometric picture here, that the determinant of this matrix here should be C. How can we convince ourselves of that algebraically? Well, let's just use sort of the defining properties of the determinant. Remember, we've got those three defining properties. So what I'm going to do is I'm going to use multilinearity on this special column in here. In particular, if I leave all of the other columns alone, I can pull that C out in front of the determinant, right? This was the third defining property of the determinant. It was property C. Okay, it was what we called multilinearity. All right, so we pull that C out in front. We're pulling it out of one of the columns. Okay, and then what we're left with is determinant of the matrix that has ones all down the diagonal, but that's the identity matrix, right? So this is C times the determinant of the identity matrix, but the identity matrix has determinant 1, so we get C times 1, which, yeah, it's just C. Okay, so this elementary matrix, it really does have determinant C, just like we guessed. All right, so that's one of the three types of elementary matrices down. Let's go on to the next one. The next type of elementary matrix is row I plus C times row J, in other words, the addition row operation. And remember what the corresponding elementary matrix looks like is, well, it looks like an identity matrix, except with a C, a single C entry somewhere in the bottom left corner or in the top right corner. All right, and geometrically, what this looks like is it looks like a shear, okay? You're sort of fixing one of the axes. Actually, you're fixing all but one of the axes, and the other one, you're sort of tilting it in the direction of another axis. Okay, so in the two-dimensional case, for example, you might be tilting sort of the y-axis in the direction of the x-axis, or, I mean, there's another type of shear. If the C was up in the top right corner, then you'd be shearing like the x-axis in the direction of the y-axis. Okay, so in this case, based on the geometric picture here, if this square has area 1, well, what's the area of this parallelogram? Well, one way to think about it is you're just taking this square here and you're tilting it over. Okay, and you're just sort of maybe slicing it into infinitely thin little slices and then sort of offsetting them from each other. So geometrically, it seems like the area of this parallelogram here should be the same as the area of this square here, right? It's just a tilted version of that square. All right, how do we convince ourselves of that algebraically though, okay? How do we convince ourselves that that determinant of that area really does equal 1? All right, well, the determinant is, again, we're gonna use multilinearity, okay? I'm gonna use multilinearity to split up this column here, this column that has two non-zero entries, 1 and C, while leaving all of the other columns alone. All right, so the way that works is you leave all the other columns alone, so just forget about them for this entire calculation. And then, well, 1, 0 plus c times 0, 1, right? There's c times 0, 1 equals 1c. Okay, so all I'm doing is I'm splitting up this column here as a linear combination of this column and this column. And multilinearity of the determinant says that's okay because I'm leaving all of the other columns fixed. All right, and now I consider these two determinants individually, this one on the left and this one on the right. And these are easier to compute. Okay, this one on the left, well, again, this is an identity matrix, right? It's just ones down the diagonal, zeros everywhere else, so that's an identity matrix. It has determinant 1. What about this matrix over here? Well, this matrix, I claim it's not invertible. Okay, and one way to see that is notice that, hey, in this row up here where we zeroed out the diagonal entry, that entire row equals 0. Okay, so when you row reduce that down to reduced row echelon form, it's still going to have a row of zeros. There's no way to get rid of that row of zeros. Okay, so its reduced row echelon form is not going to be the identity matrix, so it's not invertible. Therefore, it has determinant 0 from theorem 9.1 in our previous lecture. Another way of looking at it, if you don't like that argument, is, hey, this column right here and this column right here, those are the exact same as each other. Okay, so what's that tell us? Well, the columns are not linearly independent. The columns form a linearly dependent set. And again, we had a theorem earlier in the class that said, hey, if your columns are linearly dependent, your matrix is not invertible, therefore determinant 0. Okay. All right, and then you just add up all that junk. 1 plus c times 0, that's just 1, right? The c times 0 goes away. Okay, so yeah, the determinant of this elementary matrix that we started with, that determinant is 1. All right, 2 of the 3 elementary matrices done. We've only got one last one to go through, and that is the swap row operation, where you interchange rows I and j. And remember, this elementary matrix, it looks like this, identity, except with 2 of the rows swapped. Okay, and geometrically, what's this look like? Well, this time it's taking sort of the unit square grid to the exact same unit square grid. All that happens is you're interchanging the sides. You know, what you used to call E1 is now like E2 and vice versa, right? E1, which used to be on the x-axis, is getting mapped up here on the y-axis. And E2 that used to be up here on the y-axis is now getting mapped over here on the x-axis. So you're just sort of reflecting space. Okay. And now, based on the geometry here, we expect that the determinant is probably 1, right? It's just this area divided by this area. So let's convince ourselves of that algebraically. And this one's a little bit trickier, actually. So the way that I'm going to do this is I'm going to start off with a different matrix, okay? I'm going to start off with a matrix that's like the one we actually care about. Like, we want to figure out what the determinant of this guy up here is. I'm going to start off with this matrix down here instead, okay? So it's just got a couple extra 1s along the diagonal. And the reason I'm going to do that is because this matrix here, I can split it apart using multilinearity to get 3 matrices whose determinants I know, and the one matrix, that swap matrix up above, whose determinant I don't know and I want to figure out, so then I'll be able to solve for it, just using all of the other determinants that I know. All right, so if I split this apart using multilinearity, I'm actually going to use multilinearity twice. I'm going to use it on this column here, and I'm going to use it on this column here. Okay, and when I do that, okay, if I split up on, say, the first column, leaving the second column, leaving like this column over here alone and all the other columns alone, but then I split up on this column here, what I get is like a 1 up top and then another matrix down here where there's the 1 on the bottom. Okay, so these two here, like if I add them up, then I get 1, 1, I get the 1 in the top right and the 0 in the bottom right. Okay, and then I do a similar trick over here. If I add these two up, okay, and then what I get is 1 and 1, like this other one coming from down here. Okay, and then I'll just have 0, 1, 0, 1 on the right. Okay, and then I use multilinearity again to sort of add up those two added up matrices, and I get 1s in all the spots then when I do that. Okay, so it's just using multilinearity twice, using it on this column here and on that column, the ith column and the jth column. Okay, and now I'm going to start looking at these matrices carefully and asking, well, how do I compute each of these determinants here? Okay, the first one is easy. It's one we've done twice this video already. This one up here, this is an identity matrix, so it has determinant 1. Great, so that's 1 of the 5 determinants figured out. 3 of the other ones actually can be figured out using the exact same logic as each other, okay? So 3 of these determinants actually all equal 0. This one on the left, it has determinant 0. This one at the top has determinant 0. And this one at the bottom right has determinant 0. And why is that? Well, look at these two columns. They're multiples of each other. They're actually exactly the same as each other, okay? So columns form a linearly dependent set. The matrix is not invertible, therefore determinant 0. Same argument up here. These two columns are the same as each other, therefore columns form a linearly dependent set, therefore not invertible, therefore determinant 0. Okay, this is why we introduced all of these million different equivalences of invertible matrices, right? It lets us do arguments like this. It connects all the different topics in this course. Same thing happens over here on the left, okay? This column here and this column here, they're the same as each other. Therefore, columns form a linearly dependent set. Therefore, that matrix is not invertible. Therefore, its determinant is 0. All right, so what are we left with? I got 0 over here, 0 over here, 0 down here, 1 up here. So, I mean, this determinant plus this determinant, the sum of these two determinants has got to equal 0. But this one up here equals 1. So what does this determinant down here equal? Well, based on the picture that we drew earlier, we thought that it equaled 1, but we're seeing now algebraically, actually, it's got to equal -1. Okay, it equals -1. So what the heck is going on here? Okay, and this kind of shows that actually I've been lying to you for about a video and a half now. Okay, I said that the determinant, it measures areas or volumes, like it measures how much the matrix or linear transformation is expanding space, but that's a lie. It's not a complete lie, okay? The bulk of that statement is still true. But what it's actually doing is it's measuring signed areas or volumes, okay? And it turns out that you need to measure signed areas or volumes sort of if you want the determinant to have nice mathematical properties. If you want it to have those 3 defining properties that we started with, you know, determinant of identity is 1, and multiplicativity and multilinearity. If you want to have those 3 properties, then it needs to measure signed areas, not areas itself. And if you ever want just the area or volume, just take the absolute value of it. All right, and I mean, this maybe seems weird at first, like what the heck is a signed area? But you've done things like this before, okay? Back when you took calculus, okay, like this is completely analogous to definite integrals. Okay, remember, what is the definite integral of some function? So you got a function, you know, acting on the real numbers, and here's its graph. The definite integral of it, well, it measures areas under the graph, right? Well, no. It measures areas under the graph, but above the x-axis. And I mean, if it's below the x-axis, then you measure that negatively. In other words, it sort of measures areas, but in the sense of function value minus x-axis. All right, so the definite integral in this case, it would be like this green positive area minus this red negative area. Okay, in other words, it's a signed area. Like the definite integral, it can be negative. Okay, even though we think of it as measuring areas. Okay, making it measure signed areas gives it nicer mathematical properties and makes it easier to work with. Alrighty, well, with that technicality out of the way, I promise you, no more lies about the determinants, okay? It really does measure signed areas or volumes, okay? No more lies about it. But with that out of the way, we can now actually come up with sort of a nice simple method of computing the determinants, okay? And the way it works is, well, just string together a couple of facts that we've seen now. Determinants of elementary matrices, we know how to compute those. Okay, well, also elementary matrices, those correspond to multiplication on the left to elementary row operations, right? So every time you do an elementary row operation, you're just multiplying on the left by some elementary matrix. And also the determinant is multiplicative. So when you rephrase all of this and throw it all together, what you get is exactly this theorem here. We basically proved this theorem. We just sort of didn't write it down as a proof of a theorem. But what happens is, suppose that you've got some matrix A, you want to figure out its determinant. Well, do elementary row operations to bring it down to a simpler matrix B. Okay, and well then every time you did an elementary row operation, what happened was the determinant changed like this. If you did an addition row operation, determinant did not change at all. Okay, the determinant of those two matrices was the exact same. It didn't change. Okay, and that just corresponds to, well, if you go back up to these elementary matrices, determinants of this, remember the addition elementary matrix, we showed that its determinant was 1. In other words, what happens when you do an addition elementary row operation? Well, you multiply the determinants by 1. Okay, so it doesn't change. All right, if you do a scalar multiplication row operation, then what happens is the determinant gets multiplied by that scalar. And what that corresponds to is, well, back at the very start here, when we compute the determinant of the scalar multiplication elementary row operation, we found that its determinant was C. Okay, so if you multiply some matrix by this elementary matrix, you're multiplying its determinants by C. All right, and then last but not least, if you do a swap row operation, the determinant gets multiplied by -1, right? You just get a negative sign out in front. And again, that corresponds to this fact right here, that the determinant of the swap elementary matrix is -1. So if you multiply by that elementary matrix, the determinant gets multiplied by -1. All right, so basically, if you want to compute the determinants of a matrix, just row reduce it, row reduce it, row reduce it all the way down to the identity matrix if you can. Okay, and if you get the identity matrix, then you can just sort of trace back, well, how did I change the determinants along the way? I know the determinant of the identity matrix is 1, and well, I changed it here and here and here, so what was the determinant of my original matrix? Or maybe you row reduce it and you're not able to get down to the identity matrix. In that case, we know the matrix is not invertible, so its determinant must have been 0. All right, so let's just go through an example here. Let's illustrate this method for computing the determinants on this matrix here. Let's compute the determinants of this matrix 1, 1, 1, 1, 2, 4, 1, 3, 9. All right, so your method is the same as your method for solving linear systems. Just row reduce it as much as you can. All right, so first thing I'm going to do is I've got a leading entry in the top left. I want to zero out the stuff below it, so I just do these two addition row operations to get zeros down there. Okay, and I'm going to skip most of these row operations, or at least go over them very quickly, because we already know how to solve linear systems. We know how to do this row reduction stuff. Okay, I'm going to go all the way to reduced row echelon form. Okay, so I want to turn that leading entry 2 into a leading entry 1, because I'm going all the way to reduced row echelon form. Get rid of the non-zero entries above that last leading entry. Okay, turn them into zeros. And then last but not least, turn this non-leading entry into a 0 as well, because it's above a leading entry. Okay, and now I'm in reduced row echelon form. I certainly can't row reduce any more than that. Okay, but now I can use that previous theorem. Okay, and I can sort of trace the determinant back. Okay, what I can do is I can notice that, hey, out of all these row operations that I did, the only one that actually changed the determinants was this one on the left, the 1/2 row 3, right? Addition row operations, as far as the determinant is concerned, those are free, okay? They do not change the determinant. They multiply by 1 every time, so they don't change it, okay? So what's that tell us? Well, it tells us that, hey, this is an identity matrix. It has determinant 1, okay? This one over here has determinant 1. Well, this row operation didn't change it, so just trace it back. This matrix must have also had determinant 1. And then these row operations also did not change the determinant, so this matrix must have determinant 1. Okay, now be careful at the next step. This operation multiplied the determinant by 1/2. Okay, so if this matrix has determinant 1, that means this matrix up here has determinant 2. Okay, not 1/2, it has determinant 2, right? Because the logic goes determinant 2 multiplied by 1/2 gets determinant 1, right? So like when you're going backwards, you have to divide by this scalar, okay? Determinant 1 divided by 1/2 gets me determinant 2 up there. Okay, so since the matrix on the bottom right has determinant 1, then determinant 1, determinant 1, then determinant 2, and then again, this row operation is free, so still determinant 2. Then these row operations don't change the determinant, so this also has determinant 2. So you just trace it backwards, sort of undoing any determinant changes that you made along the way, and you find that the original matrix had determinant 1 divided by 1/2, which is 2. All right, and one sort of neat thing that happens that's sort of suggested by this example here is if you look at this matrix here, we said that this matrix has determinant 2, and that's exactly 1 times 1 times 2. It's the product of the diagonal entries of that matrix. And it turns out that this is a general phenomenon, okay? But the special property of the matrix that you need for this phenomenon to happen is the matrix has to be upper triangular, okay? We've got zeros down here in the bottom left corner. Okay, but in that case, the determinant is actually just the product of the diagonal entries. Okay, so we're going to state this as a theorem and we're going to prove it. And the reason that this is nice is then we don't need to go all the way to reduced row echelon form to get the determinant. We don't need to do these last 3 steps. We could stop when we get to row echelon form like up here and then just say, oh great, now the determinant is 1 times 1 times 2. All right, so theorem time. And it's just going to state what I just said there. Suppose that you've got any triangular matrix. So it can be upper triangular, it can have non-zero entries in the bottom left, or it can be lower triangular, it can have all 0 entries in the top right. then the determinants is really easy to compute in this case. The determinant, it's just the product of the diagonal entries. So it's A11 times A22 times A33 all the way up to ANN. All right. So let's prove this guy. Where does this come from? And we're not going to do a complete proof, but we'll at least do enough to give you the idea of it. Where it comes from is, well, you can just take any upper triangular matrix and you can do a very simple sequence of row operations to it to turn it into the identity matrix. Okay, so the idea here is, suppose that you've got some upper triangular matrix. Okay, the same argument works if it's lower triangular. I'm just going to do it as if it's upper triangular though. Okay, then what I'm going to do is I want to turn this into the identity matrix. The first thing towards that is I'm just going to rescale each of the columns so that these leading entries are now 1s instead of whatever they are. Okay, I'm going to divide row 1 by A11, divide row 2 by A22, all the way up to divide row n by ANN. Then I'll have the identity down the diagonal, still zeros in the bottom left, and, well, some junk up in the top right. And I don't particularly care what junk is up in the top right because it's not going to matter. Okay, whatever junk is up in the top right, I can now get rid of it just via addition row operations, right? If I want to get rid of sort of the entry directly above the 1, just add a multiple of this bottom row to it. Okay, and in general, I mean, add some multiple of this bottom row to all of these entries in here to zero them out. Okay, and I'll zero out the rightmost column. And then you just go up backwards, up the back of that diagonal. There will be a 1 here. Add some multiple of it to these entries, okay? And just work backwards, rightmost column to leftmost column. And you can zero out all of these entries just with addition row operations. Okay, and then after those addition row operations, you'll be row reduced all the way down to the identity matrix. Okay, so if you want to figure out the determinants of the original matrix, you just sort of start at the right-hand side here. Determinant of the identity, that equals 1. Okay, and then trace things backwards. Okay, addition row operations, those did not change the determinants, so this matrix also has determinant 1. And now trace things back one more step. Well, these row operations did change the determinants, okay? And how much? Well, it multiplied the determinant by 1 over A11, and it multiplied the determinant by 1 over A22, and it multiplied the determinant by 1 over ANN. And I mean, when you combine all of those, and remember that you're sort of undoing that change, you find that the determinants of this matrix had to be the product of all those diagonal entries. It was A11 times A22 times ANN, times all of them, right? Okay, and remember, when you're going backwards, you divide by what the determinant is changing by. So we're dividing by 1 over A11. So we're multiplying by A11, and so on. All right, so yeah, so this original upper triangular matrix, its determinant is just the product of all of those diagonal entries. Okay, except I lied and cheated a little bit in the proof of this theorem. And what I lied about was, well, I assumed that each of these diagonal entries was non-zero. I assumed that I could divide by them. So what happens if one of them does equal 0? Well, it turns out the theorem, fortunately, it still is true in that case. So what the theorem says in that case is that the determinant of A is going to equal 0, right? Because if one of these diagonal entries is 0, then the product of all of them is 0. So in other words, what the theorem's saying is if it's upper triangular with a 0 diagonal entry, then it's not invertible. Okay, and that's true, okay? That's maybe like an exercise left to the reader. That's something you can try to prove on your own, but hopefully it should seem a little bit believable, right? If you've got a 0 diagonal entry somewhere, then what's going to happen is that column that has a 0 diagonal entry, you're going to be able to write it as a linear combination of all the columns that came before it. Okay, so the matrix is not going to be invertible for that reason. One of the columns is a linear combination of the others, so the columns are not linearly independent, so the matrix is not invertible. All right, so we're just going to leave that sort of as an aside that we're going to gloss over. If one of the diagonal entries equals 0, matrix is not invertible, theorem is still true. Okay. All right, anyway, with all that out of the way, let's do one final example where we actually make use of this method to compute the determinant of a matrix, okay? And this time we're going to do basically the same thing that we did in the previous example, except now we're not going to go all the way to reduced row echelon form. We're only going to go to row echelon form, and this will make the computation a little bit quicker. All right, so we're going to compute the determinant of this lovely matrix here. And again, same thing as always, okay? To get in row echelon form, just do the same junk that we did when trying to solve linear systems, okay? Just do Gaussian elimination. Identify your leading entries. Leading entry is in the top left corner there. I want to get zeros all below it. Well, I've already got 2 zeros. I just need to zero out the 1 here. That's why I do this addition row operation to get a 0 there. And move on to the next leading entry, this -1. Get zeros below it. Okay, so that's going to be 2 addition row operations to get rid of these 2 non-zero entries. 0, 0, boom, we're happy. Okay, and now next leading entry is over here. We want to get rid of the non-zero entry below it, so that's one addition row operation. Boom, we got a 0 down there. And now our matrix is in row echelon form. In other words, it's upper triangular, so we can apply the previous theorem, okay? And actually, we're going to combine our two previous theorems, okay? So one of the first previous theorem, the theorem about upper triangular matrices, tells us that, hey, the determinant of this matrix is 3 times 2 times minus 1 times 1. In other words, the determinant of this matrix down here is minus 6. You just multiply together the diagonal entries, okay? And the theorem from before that told us that, hey, we only used addition row operations to change this matrix, and addition row operations, they don't change the determinant. They're free as far as the determinant is concerned. So if the determinant down here is minus 6, so is this one, so is this one, and so is this one. So in particular, this matrix that we started with, this matrix A, it has determinants equal to minus 6 as well. All right, so since the last matrix has determinant minus 6, so does the original matrix. Determinant of that starting matrix A is minus 6 as well. Okay, so you just row reduce down to row echelon form now. Compute the determinant using that theorem about triangular matrices, and then trace your changes back to the original matrix. And if you do any swap or scalar multiplication row operations, then you have to make adjustments. But a lot of the time, you can get away with just doing addition row operations, and those don't change the determinant, so they're really easy to deal with. All right, fantastic. So that does it for today's lecture. We're done with sort of the best and quickest method for computing the determinant. What we're going to do next class is we're going to introduce some explicit formulas for the determinant. And these formulas, they're going to be really handy for 2x2 and 3x3 matrices. For larger matrices, they're not as practical, but they still serve some theoretical use. We're going to need them next week to be able to do some computations that are tricky with this method here. So anyway, we're going to see another method of computing determinants next time. I'll see you then for that.